A faster, more efficient, more powerful car is perceived to be a better car, so the question is, how do you increase the power? One way of increasing the engine's performance without increasing the size of the engine is to achieve bigger explosions in the engine's combustion chamber. Bigger explosions are achieved by burning more fuel whilst maintaining the fuel-to-air ratio in the combustion chamber. This means a higher mass of air is required within a fixed volume. The only way this can be done is by compressing the air. This is accomplished by forced induction. The types of forced induction are supercharging and turbocharging. The difference between these processes is that a supercharger is mechanically driven by the engine's crankshaft, whereas a turbocharger is powered by the mass flow of exhaust gas driving the turbine.
In the 1860s, Francis Root invented and patented a twin-rotor industrial air mover. This was the foundation of the Root-style blower still in use today. In 1885, Gottlieb Daimler obtained a patent for a pump that aided the delivery of increased amounts of air and fuel to the cylinder of an internal combustion engine. Another engineer called Craigen invented an air pump that utilized twin rotating shafts that compressed the air. This technology would go on to become the foundation of the Lewisham twin-screw compressor. Turbochargers were patented by Dr. Alfred Bucci in 1905. His idea was first used by General Electric in 1910 on a diesel engine. These turned out to be inefficient and were never used. In World War II, major advancements were made. At high altitudes, internal combustion engines that worked great on the ground suffered in the thinner air. With the addition of forced induction, this problem was overcome. The Allied forces had the supercharged Supermarine, Spitfire and the B-36 that claimed in the handbook to need 90 cylinders instead of the actual 28 if the turbo was not used. The first successful turbocharged automobiles were the Mercedes-Benz 300 ST and the VW Golf Turbo Diesel that were released in 1981. In 1982 to 86, they also used to push Group B rally cars to 1,000 brake horsepower until they were banned after a series of major accidents, some fatal, and were blamed on the outright speed. After 2 seasons of F1 turbocharged cars, in 1989 they were banned to reduce engine power output and thus speeds.
I'm Phil Gascoigne.
I'm Ronnie Alseni.
And we're here to look at superchargers and turbochargers.
We're going to have a look at the different components that make up both.
I'm going to go down and get some external views and opinions from people on the two.
And now we're going to have a closer look at the supercharger. Okay, there's different types of superchargers, displacement type superchargers and centrifugal type superchargers. Here, one example is the Roots blower. This has counter-rotating lobes that are usually self-lubricated and which move around the air from the fill side to the discharge side. They were originally designed for use in industrial buildings for providing air movement. The other example is the twin screw. Again, it has 2 counter-rotating meshing screws that have a decreasing cross-sectional area as you move towards the back of the twin screw. This compresses the air as it moves back and out through the discharge side. Here's an animation of the Roots type supercharger in action. In this animation, the air passes through a butterfly valve controlled by the throttle that regulates the air supply to the Roots supercharger. The air gets trapped by the 2 counter-rotating lobes from the intake side and moves around the casing, and this is displaced through the outlet, moving a fixed volume of air per rotation. This is commonly known as positive displacement. The hot air has to be cooled before entering the intake manifold of the engine. This is done by the intercooler. To eliminate the problems of surge, a bypass valve, sometimes called an anti-surge valve, is used to release the excess pressure. Centrifugal supercharger. This operates like a high-speed fan. It sucks air into the center of the supercharger and pushes air out. Air naturally travels to the outside of the blade due to the centrifugal forces created by the rotating inertia. At the outside of the blade, a screw is waiting to catch the air molecules. Just before entering the screw, air molecules are forced to travel through the venturi that creates the internal compression. As air travels around the screw, the diameter of the screw increases. This slows down the velocity of the air, hence increasing the pressure. Right. Here's an example of a displacement type supercharger known as a Roots blower. Here the engine crankshaft is directly coupled to this driving gear and hence in turn coupled to the driven gear. The driven gear is smaller than the driving gear, making the intermeshing lobes of the supercharger move much faster than the crankshaft. The rotors of the screw compress around without touching each other, or the casting like those of the Roots blower, whose efficiency drops rapidly with increasing pressure, but the gaps are left as small as possible. The air enters the concave space in the rotor and is compressed by the convex threads on its way from the inlet to the outlet of the compressor. Pressurized air from the compressor comes in through the inlet, passes through a matrix that's usually made of copper while cooling down, and leaves through the outlet that goes to the intake manifold of the engine.
After Semi was in the lab, I then went down to have a look at turbocharger components. As you see in this animation, the turbocharger works in the same way as a centrifugal supercharger, but it is driven by the engine's exhaust fumes rather than the crankshaft. This is a compressor. The air enters the compressor at this end and flows around the tube. The cross-sectional area of the tube decreases, as you can see here on this cross-section, which means the volume of the air in the tube also decreases, but the flow rate of air is constant. This increases the pressure of the air, hence the name compressor. The compressor cover is usually made from cast aluminium alloy. This is usually manufactured by gravity die and sand casting techniques. All turbochargers have this compressor, but is also used on the centrifugal supercharger. The turbine is driven by exhaust fumes, which enter radially and leave axially. The turbine is coupled to the impeller via the shaft. The impeller blades are shaped differently to the turbines, which push air out radially, hence drawing it in axially, putting an axial force on the shaft. The shaft has a stopper attached to it. There is a thrust bearing positioned behind the stopper, which provides a counteracting force, so the net force on the shaft at any time is zero. The turbine wheel is made from a nickel-based superalloy by investment casting. This method gives accurate turbine blade sections. Large units are cast individually, whereas smaller ones can be cast in numbers using a tree configuration. The shaft connecting the turbines is made from forged steel. It is friction welded to the turbine wheel. Impellers are produced using a variety of the aluminium investment casting processes. Here we have a turbine housing with a wastegate, which is a type of internal bypass system. This controls the boost pressure at higher engine speeds. It does this by opening a valve controlled by the vacuum or pressure actuator that diverts excess pressure from the turbo into the exhaust, like so. In this way, the wastegate serves to regulate and protect the engine and turbocharger from any excess boost pressure. We're now going to do a comparison of many of the aspects of turbochargers and superchargers.
Power outputs on superchargers and turbochargers are dependent on the boost pressure. Boost pressures are dependent on how fast the compressor spins. Usually on superchargers, it ranges from 30,000 RPM. This would in turn give an additional 6 to 9 psi. Boost pressure.
Turbochargers, on the other hand, have an average RPM of about 150,000. This gives them an additional 25 psi boost pressure. This gives them a much higher output than the supercharger.
Efficiency in superchargers is usually reduced since they have a parasitic effect on the engine. This roughly is about 20% lost due to frictional losses in the belt.
On the other hand, turbochargers don't have this parasitic effect because they're driven by the engine's exhaust gas. There is a slight inefficiency where the piston has to push some of the exhaust gas through the turbine.
Most superchargers don't need intercoolers since the operating boost pressure is quite low, usually under 10 psi.
The turbocharger is mounted to the exhaust manifold, which is very hot, so the gas inside expands, so it needs to be cooled. So an intercooler is required on nearly all turbochargers.
Superchargers are more reliable than turbochargers. This is usually the case since superchargers have less moving parts than turbochargers, hence less wear can be caused. This reduces the cost of maintenance and repair. Superchargers also operate in less harsh conditions than turbochargers do. This has a dramatic effect on the lifespan of the supercharger.
In a turbocharger, there's a surge of power around 3,000 RPM when the wastegate's open. This can be damaging to the vehicle's engine and make the vehicle difficult to drive. Back pressure in the turbocharger means a loss in power and reduces overall efficiency.
Superchargers are relatively easy to install. There are fewer components than turbochargers and simpler devices.
Turbochargers require manifold and exhaust modifications, intercoolers and extra oil lines, as well as tapping into the oil pan of the engine.
Superchargers require little or no tuning. Sometimes they only require separate fuel and ignition upgrades.
Turbochargers are difficult to tune as they're complex and they rely on variable compression ratios. Our conclusion is that it totally depends on your preference as to whether superchargers or turbochargers are better. All we can say for certain is that performance improvement initially drove the forced induction revolution, whereas today fuel consumption and emission control have become the main focus and are leading further development into the future.